energy. You know you've got it because you're able to do work, like moving your legs to ride a bike. A moving freight train has energy too. You can see it do work, pulling freight cars along the track. Everyone is familiar with the word energy, yet few people really understand what it is. That is because energy is so different from matter, in that it doesn't have mass. We can observe energy's effect on matter by using our senses, and we can also examine how it is converted from one form to another. Energy is the ability to do work.
By the end of this program, you should discover the relationship between kinetic and potential energy of a system and how thermal equilibrium applies to the system, as in a cup of tea. You'll learn how to apply the first law of thermodynamics to systems and to a bike ride. And you'll learn how energy changes can be measured, assigning the SI unit of joule to these energy changes. You'll learn the meaning of the terms endothermic and exothermic. And you'll see some cool stuff, like how this flask can lift this stool right off the ground.
Basically, there are two kinds of energy that matter can have. Fred, do you know what the two kinds are?
Well, one of them is kinetic energy.
That's right.
And the other one would be potential energy.
Exactly. Now, kinetic energy is the energy of molecular movement.
Right. So then this cup of tea would be an example of that, because the molecules in the system are in motion. Right?
Correct. Now, as the system cools, the average molecular speed slows down. Therefore, the molecules have less kinetic energy. But if we heat the system, the average speed of the molecules increases. Therefore, the kinetic energy increases. Potential energy is stored energy. For example, Fred, when you lift this helmet, you're expending energy. The energy now is stored. Where?
It must be stored in the helmet.
Right, it's stored as potential energy. Now, if you drop the helmet, it loses gravitational potential energy.
So then an object like this apple must have energy too.
Yes, but what kind? Kinetic or potential?
It must be potential energy.
Okay, good choice. It is potential energy, but a different kind that's called chemical potential energy. Now, the chemical potential energy is stored in the chemicals that you eat. And it's released during the chemical reactions involved with metabolism. This energy is ultimately converted to the movements of our muscles and to body heat. And there are other kinds of energy conversions with a bit more sparkle to them.
Usually when we're dealing with high explosive like this, we will have about 100-meter distance that we will set up our command post, our initiation center at, and we find that that's a safe location for us.
Are explosives rated in terms of their yield? How much energy comes out of them?
Yeah, they're rated as either a high explosive or a low explosive. A low explosive basically is a deflagrating explosive, combustion. A high explosive has a detonation velocity of over 1,000 meters a second, and it's considered instantaneous detonation. They're both combustion, it's just the rate of combustion.
I notice you're spending an awful lot of time on safety now. I know why that is, but fill me in anyway.
Okay, whenever you're dealing with explosives, you have to handle them with extreme caution because of the amount of energy that can be released when you're initiated. What we're going to be setting off here right away is a high explosive. And whenever we deal with high explosives, we make sure we have at least a minimum of 100 meters working distance. That way we don't have to be worried about the pressure wave or any fragmentation that may come from ground zero there where we're setting it off.
So in other words, you don't take for granted the amount of energy that's inside these devices?
Absolutely not.
Okay. So you're carrying the detonator?
Yes.
And he's carrying
the explosive charge.
So why is he standing so far back?
Well, it's important for safety reasons that we keep the detonator and the explosives apart until the very last moment when we bring them together and then initiate them. It's a safety factor. We would always get at least a minimum of 25 feet between each other.
As a chemistry teacher, I'd tell you energy can be neither created nor destroyed, only converted from one form to another. This explosive device, the chemical energy in the bonds, is going to be converted into what forms?
Okay, when the the explosive is initiated, it takes about 1/10,000th of a second for the energy to be released. When the chemical reaction occurs, what happens is there's expanding gas from the seat of the explosion. The seat of those expanding gases form a shock front, which is known as a pressure wave. Accompanying effects after that are light, noise, and
Heat? Heat. Now, the most destructive form in terms of the explosive of those forms you just said is
the shock wave,
the pressure wave. And that's actually air molecules driven out by the force of the hot expanding gases and impacting into other things.
Right.
That's what does the damage.
Okay, what I'm going to do now is I'm going to be hooking up the detonator into the line that I checked, and you saw me check it for continuity.
Right.
Once I do that, then I'm going to be placing the initiator into the explosive, which my partner has brought down here. Once the two are connected, I'm going to be going back to where the reel is, and I'll do another continuity check just to make sure everything is in line and there's no breakage in the line itself. So. Continuity. Bob, check the area. Make sure there isn't anybody around. Clear? Charging. Firing! 3, 2, 1.
So, John, what's going to be the difference between this and what we just saw?
Okay, with the smokeless propellant here, it basically deflagrates. The other explosive that you saw, it detonates. And basically, the difference between the two of them is just the combustion rate.
Oh, so in other words, the energy still gets released, it just gets released over a longer period of time?
That's right.
Is that why there's no pressure wave built up like we saw on the other one?
That's right. With the high explosive, you have instantaneous detonation, which gives you that shock wave. With this, it's very slow burning, and there is no shock wave that accompanies it.
Okay.
Energy is never lost. It's just converted from one form to another. And you don't need explosives to demonstrate this. Thermal energy is one form of energy. When thermal energy is transferred, we call it heat. Let's use a cup of tea to explain how heat transfer occurs, resulting in thermal equilibrium.
This tea is too hot. I'll just add a little bit of cold water.
Here's what's happening in the tea. Fast-moving hot water molecules have higher average kinetic energy than the slower-moving cold water molecules. When the hot water molecules collide with the cold water molecules, the hot water molecules transfer some of their kinetic energy to the cold water. The effect is that the fast hot molecules lower their average speed and kinetic energy, while the slower cold molecules increase their average speed and kinetic energy, until most of the molecules in the system have the same average kinetic energy. This will result in a uniform temperature of the tea, which, at this point, is referred to as thermal equilibrium.
So the thermal energy traveled from the hot water to the cold water I just added.
That's right.
But that's just another way of saying that the tea has a cooler temperature, right?
Well, it's important to distinguish between heat and temperature. Let's have a look. Temperature is a property that reflects the random motion of particles in a specific substance.
Well, the substance we just examined was my tea, but I still don't understand.
Well, the hot water molecules in the tea are in motion. If we put a thermometer in the tea and take its temperature, this is an indirect measurement of the motion of the hot water molecules.
So increased motion, increased temperature.
That's right.
But what about heat? How does heat fit in with temperature?
Well, if there is a temperature difference between two objects,
Like my tea and the cold water.
that's right, then we can say heat involves the transfer of thermal energy between two objects due to a temperature difference.
Thanks, I understand now.
All right, how's your tea?
Better.
Good.
We know energy is always conserved, and heat, which is just thermal energy transferred, always moves from a hot object to a cold one. But we need terms to describe whether a substance is gaining or losing energy. The terms we use are endothermic and exothermic. An endothermic change can be described as one in which energy is absorbed by a system from its surroundings. As a matter of fact, we break the word down. Endo means in, and thermic means heat. Heat, in. Now, I've got something to show you, a very dramatic example of an endothermic change. It's so dramatic, I need a few props. There we go. The reason why it's so dramatic is it's almost magical. Now, what I have here is some solid ammonium thiocyanate. And I'm going to pour this solid ammonium thiocyanate into this very large 2-liter Erlenmeyer flask. Next, I have some solid barium hydroxide octahydrate. That solid also goes into the same flask. All right, now, watch. Magic? We shall see. Now, when I start shaking this vigorously, you'll see something really special happen. Oh, and I have to put some water on there. Lots of water on that table. There, that should do. Now, the solids have turned into a liquid. Now, while we're looking at that, and by the way, the camera's going to stay on this for a while, we'll look at some other different examples of endothermic changes. For example, a battery being charged is undergoing an endothermic change. Energy from an external source is converted to chemical potential energy stored in the battery. We also have here some ice cream, some melting, or rather melted strawberry ice cream. And this too is an example of an endothermic change. The frozen ice cream is absorbing energy from its surroundings in order to melt. Now, as far as this plant is concerned, photosynthesis is also endothermic. The plant absorbs energy from the sun. Okay, let's have a look at this. And just to make sure that it is all on the level, no wires anywhere. Is it magic? Well, I'll tell you what. Let's look at the chemistry that's actually happening in there, and maybe we'll learn something. Now, the solid barium hydroxide octahydrate that I used comes with its own built-in water. So when it reacts with the ammonium thiocyanate, a solution forms. And the formation of this solution is endothermic. And this endothermic change absorbs energy from the surroundings, including the water on the tabletop. Now, if you look very closely at where this flask is sitting on the table, you can see something. I see ice. So this change was so dramatic that what happened was that the water literally froze the flask to the top of the stool. And that's how I can lift it up. Magic? No. Just neat science.
In the endothermic process you just observed, energy was absorbed by the system. But a change in which energy is released by a system to its surroundings is called an exothermic change. If we break that word down, exo means out, and thermic means heat. You see examples of exothermic changes all the time. For example, the chemical potential energy from the combustion of gasoline in your car is transferred to mechanical energy that drives the wheels. Chemical potential energy is also transferred to sound, as well as heat that's removed by the radiator. We can experience an exothermic phase change when it snows. As the water droplets in the clouds freeze into snowflakes, energy is released by the water. This is why it feels warmer when it snows. Another example of exothermic change is a nuclear reaction, which releases tremendous amounts of energy. Nuclear reactors are designed to control reactions so that the energy can be released safely. Some exothermic chemical changes can be used to create works of art. Let's have a look.
Blacksmithing is a lot of different things, but for us, we're artist blacksmiths, so we take coal and steel and are able to create other objects out of them. Well, I love to take all the dimensions of the old art form and bring them and update them. I do restoration work, so I have to be versed in the old ways and old materials and everything else, but I use this as a method of personal self-expression in transforming steel, making it do exactly what I want it to do. We're taking coal, putting it on this table, and igniting it, and then using air supply, which you saw in the old days was either a hand cranked or a bellows. We're using an electric fan to pump air through it. And the volume of air we flow through it increases the temperature proportionately. We can get it up to 1300 degrees Celsius, which is enough to start steel burning instead of melting. We use the purest form of coal we can find because we're converting that coal into coke, which is just almost pure carbon, and that's exactly what we want to burn in a blacksmith's fire. Flux is our generic term for any antioxidant. In other words, it's boric acid, and it's extremely corrosive when it gets to that heat, so it takes off all the scale, or that oxidized material, and leaves us with fresh, clean metal to join together. We take steel through a phase change. We take it from a solid to a liquid in order to form that bond. A lot of welding is you have to add something to it. We only have the amount of material that we have when we start.
In any exothermic reaction, energy is produced by the reaction, released by the reaction, and absorbed by the surroundings. In this case, the surroundings around the fire, and more importantly, the metal piece that the blacksmith puts in so that he can heat it up and work it. Endothermic and exothermic phase changes can work together. This refrigerator freezer is an example. If I want to freeze the water in this tray into ice cubes, energy has to be released from the water. That's an exothermic change. Where does this energy go? I can use this camera to show you. Inside the freezer compartment are some coils, and they carry a liquid. And the energy that's released from the water is absorbed by the liquid in the coils. This vaporizes the liquid in the coils. That's an endothermic phase change. The vapor is then routed to the back of the fridge, which we'll go take a look at right now. And routed down through the coils to the condenser. The condenser liquefies the refrigerant, and that's an exothermic phase change. Where does this energy go? Well, it's released to the surroundings, the back of the fridge and the air, and that's why it's warm at the back of a refrigerator. Let's summarize. With endothermic changes, the energy of the system increases. Thermal energy is absorbed, and the temperature of the surroundings decreases. For example, ice cream melting is an endothermic change. With exothermic changes, the energy of the system decreases, thermal energy is given off or released, and the temperature of the surroundings increases. Combustion is an exothermic change.
This beetle is armed and dangerous. Nature provides many intriguing natural defenses, but the bombardier beetle system of defense is literally too hot to handle. It's derived from chemicals and is a very unusual example of exothermic change. Watch this encounter between a toad and a bombardier beetle. Toads feed by striking and swallowing their prey in one motion. But here, the toad strikes the beetle and almost immediately gets rid of it. This is because the beetle is able to direct a chemical spray which is pulsed from its abdomen. When threatened, the beetle combines two chemicals in a pair of special glands in its abdomen. Each gland is composed of two chambers. The upper, larger chamber stores hydroquinones and hydrogen peroxide. The smaller, reaction chamber, contains enzymes. When the beetle is attacked, the upper chamber is compressed, forcing the two chemicals into the smaller reaction chamber. Here, enzymes set off explosive pulses of hot quinones at 95 degrees Celsius, which are aimed at the attacker. Can you suggest why the beetle fires off a series of tiny explosions instead of one big burst? It has to do with exothermic heat production. If the reaction chambers were large, the chemicals would produce too much heat, and the beetle would be burned by its own chemical reactions. A small reaction chamber allows for smaller amounts of chemicals to mix and be expelled in short bursts. An exothermic chemical change as a defense mechanism. It's an ingenious system, and it makes this beetle too hot to handle for the average predator.
So far we've looked at a variety of energy changes. Now we have to consider a way of measuring these changes. Now, we all know that if you rub your hands together, they get warm. That's because you're doing work. And work is the transfer of energy, in this case, thermal energy in the form of heat. And the harder you press, the more friction you develop. Now, friction is defined as the resistance to relative motion between two bodies in contact. And the harder you press, like I said before, the more heat you develop from the friction. Hey, Stephanie, what are you doing up there?
Demonstrating friction.
Well, after that grand entrance, I've got a question for you. Can you think of another dramatic way in which friction can be demonstrated?
Well, when a meteorite hits the Earth's atmosphere, it rubs against all the gases and creates a big ball of fire.
Good one. The point is, work of any kind, mechanical, electrical, or chemical, produces heat. This was confirmed by James Prescott Joule, a British physicist from the mid-1800s. Now, Joule was the son of a wealthy brewer, and because of this money, he had time to do things that he liked. So even though he worked in the family business, he loved to spend time experimenting. And one of his experiments involved little more than stirring water. Looks pretty simple, right? But Joule determined the mechanical equivalent of heat by measuring the rise in temperature produced in water by stirring it. As a tribute, the scientific community made the joule the standard unit for measuring any type of energy change. So now we say that the quantity of heat required to raise the temperature of 1 gram of water 1 degree Celsius is 4.19 joules. Joule is the unit used in SI, the international system. However, there are other units used in other systems. For example, the unit commonly used to measure energy in food is called the calorie. You'll see it on nutritional labels. And the unit used to measure the energy output in a furnace or gas stove in your home is the BTU, the British Thermal Unit. However, the joule is the standard unit we use in science to measure any type of energy change, whether it's fuel combusting, hot tea cooling off, a train pulling freight, or cyclists pedaling down a country road. So let's review by seeing how many changes of energy we can find here in the great outdoors.
Boy, am I getting tired. Riding my bike over all these rough roads sure does take a lot of energy.
And the sun is getting hotter by the minute.
Nice garden.
Yeah, a lot of potatoes. In the fall, I have to dig them up.
Speaking of potatoes, I'm hungry. Pass the chips. Thanks.
This is a lot of work. If I was a car, my radiator would be boiling over.
All of these conversions of energy are examples of the first law of thermodynamics, which states that energy cannot be created or destroyed, only converted from one form to another.
I need a cold pop. Who's the pop?
Take
the last one.
We have only seen a few examples of energy change that occurs all around us. They all follow the principles of thermodynamics. Heat always flows from hot to cold, and energy is always conserved. When heat energy is transferred between a system and its surroundings, the change is either endothermic, absorbing energy from the surroundings, or exothermic, releasing energy to the surroundings. As well, systems tend toward thermal equilibrium, where molecules of the system have the same average kinetic energy, resulting in a uniform temperature. Finally, the unit we use to measure energy is the joule. Energy is difficult to define precisely, but we can follow its conversions. Even though energy has no mass, we can detect it with our senses because of its effect on matter. Energy affects every moment of our lives. I went great!
You have just seen the introductory program in this unit on thermochemical changes. There are 14 programs in the unit, each concerned with a particular aspect of thermochemical change. Water warms and cools slowly compared to other substances. This helps living organisms, like my friend Irving here, that have a high water content, maintain a relatively constant body temperature.
And we could place the apparatus really close to the burning peanut, so that less energy would be lost into the air around it. Great. That's good.
Great. Position.
There. All right. Oh, that's burning good. Yeah.
Sublimation is defined as the change from a solid to a gas without passing through the liquid state. And sublimation is a process by which freeze-dried food, like this, is made. This food is put into a chamber where the pressure is below the vapor pressure of ice, and this causes ice crystals to sublime. So when you're ready to eat, just add water.
Have
you ever wondered about the exothermic formation of a salt solution? Well, if you've ever driven on an icy winter road, you'd probably like and dislike this solution.
The Zamboni drives across the ice, coating it with 580 liters of water at 60 degrees Celsius. This water cools to zero, then freezes. Once this ice layer is formed, it cools further to reach the same temperature, about minus 10 degrees Celsius, as the ice layer below, establishing thermal equilibrium.
Go for main engine start. 3 main engines up and burning. 3, 2, 1, 0, and liftoff of the Space Shuttle Discovery and the Upper Atmosphere Research Satellite, studying the Earth's environment from space.
Roger, roll, Discovery.
Diamonds, precious gems, a symbol of love. Show her how much you care. It'll only cost a couple of months' salary, but by using Hess's law, why couldn't we make our own diamonds? Just take graphite, that's the stuff that's in pencils, and turn it into diamond. Easy, right? After all, they're both forms of carbon.
Acid rain is a major problem in many parts of the world. Coal-burning factories and motor vehicle exhaust release sulfur dioxide and nitrogen oxides into the atmosphere. These react with water to produce sulfurous, sulfuric, nitrous, and nitric acids. The process of turning iron ore into steel is a complex one, involving a number of thermochemical changes.
What are we doing here? It's freezing!
Listen, sometimes you gotta go and find chemistry. It just isn't in notebooks and blackboards. And what better place? I want you to do a calculation to find the molar enthalpy of combustion of octane.
There are several things that make these windows more efficient than standard windows.
How much more efficient would they be?
Probably 30 to 40%.
Well, there's a lot of science in these windows.
Definitely.
What are you doing?
I'm attempting to solve the case of the missing moths.
But what does that have to do with nuclear changes?
Well, it's elementary. Matter and energy are interconvertible.
And think about this. Which is actually riskier? Smoking cigarettes or living next door to a nuclear power plant?
We have to come to a decision. Which alternative should we choose? After careful consideration, we...
Chemical potential energy is stored in the chemicals we eat.
Like I said before, the harder you push, the more pressure you have developing friction and heat. Hey, Stephanie, what are you doing up there anyway?
Demonstrating friction. Chemical potential energy is stored in the chemicals we eat. Chemical potential energy is stored in the chemicals we eat. And there are other kinds of energy conversions with a bit more sparkle to them. How's your tea?
Much better.
Okay, good.